Our sun influences us down here on Earth in many ways beyond just providing light and heat. Storms on the sun can cause disruptions to our communication and electrical distribution infrastructure. Its UV rays can cause cancer. And wind from the sun would strip gases from our atmosphere if we had no magnetic field. In this part of our unit you will learn more about the Sun-Earth connection. Space in windy. Yes, there is space weather. Every second, 1.5 million tons of matter blow off the sun. This solar wind is made of high-energy particles, including protons, electrons, and alpha particles. The solar wind gets gusty at times, with more matter streaming away after a solar flare or a coronal mass ejection. More material also billows away through magnetic funnels that form phenomena known as coronal holes. The solar wind befriends our magnetic field, causing electrical currents in the upper atmosphere, and aurora. Our sun is a dynamic star. The sun is mostly fluid hot plasma, and it rotates. Due to its rotation, its magnetic field is very complex. Magnetic field lines are twisted, stretched, and interact with each other. Where field lines of a magnetic loop leave and re-enter the photosphere, convection from below is reduced, cooling that small patch of photosphere. Being cooler, it appears darker. These dark patches are called sunspots. Sometimes, twisted and kinked magnetic field lines snap, releasing huge amounts of energy in a flash. These events are so hot that a lot of the energy comes out as X-rays. These eruptions from the photosphere enrich the solar wind, causing gusts. If this enriched solar wind hits our planet's magnetosphere, we can sometimes see the northern lights here in central Michigan. CMEs, or coronal mass ejections, are similar to solar flares but are much more massive explosions that originate from highly twisted magnetic field structures in the corona. One of the largest of these, seen by British astronomer Richard Carrington, occurred in 1859. It was so powerful that auroras were seen as far south as Cuba. Telegraph systems were disrupted. If a similar CME occurred today, it could knock out our electric power for months. Coronal holes are openings in the sun's magnetic field that allows more plasma to flow out on the solar wind. This increase in density and speed of the solar wind can trigger auroras on Earth. Our planet is protected from the effects of the solar wind by our defense shield, the magnetosphere. Energetic particles in the solar wind are deflected around the planet. Strong electrical currents induced in our upper atmosphere by the solar wind can cause gas atoms in the atmosphere to glow, producing the northern lights. Maybe someday some of you will be able to get this view of the aurora from orbit. Solar activity has many impacts on us here on Earth. This chart illustrates those effects. Solar cells that provide power to our satellites can be damaged. The upper atmosphere can expand, causing increased drag on low-orbiting satellites. This could cause them to re-enter the atmosphere and burn up. Electric current in the ionosphere can disrupt communication. Transformers can short out, causing blackouts. Astronauts sometimes have to take shelter to avoid increased radiation. As you can see, the effects are many. NASA, ESA, the European Space Agency, and JAXA, a Japanese space agency, all have satellite missions in space that are part of an ongoing study of heliophysics. Heliophysics is a study of the sun, and its influences on our planet. The Themis satellites launched in 2007. The mission used 5 separate satellites, each equipped with instruments called magnetometers, to monitor changes in the Earth's magnetosphere in response to solar storms. The mission included ground station magnetometers, even in schools found in 11 northern states. Our school was fortunate to be selected as the site of a ground station magnetometer as part of NASA's Themis mission. Students from our school helped install our magnetometer in the field next to the cross-country course back in 2005. The images at the top of this slide show data received from our ground station. This was a fairly quiet day, but you can see that the strength of the magnetic field here in Remus varied over the course of day. The bottom image shows what is called the KP index. KP indices show the relative strength of solar influences on our planet's magnetic field. The taller the bar on the graph, the stronger the impact. KP of 5 or higher means there might be an aurora visible by us, at night, of course. Alaska is farther north, and shows stronger variations in Earth's magnetic field. Another school in Petersburg shows strong changes in the field. And look at KP. There should have been aurora visible that night, if it was clear. In class, we are going to do a series of activities to investigate how magnetic fields form. I'm looking forward to it. Are you?